what we have here is a triangular pyramid. The base is a right triangle, so here's the 90 degrees, and the legs are of lengths A and B, so let's call this one A and this one B, and the height is C. And what I've done is I've put the height along the x-axis. This is the x-axis going upwards, so that means that this point here, the apex, is the point where x is equal to C, and this is the origin. Okay, now I allowed us to assume that the apex is directly above, so everything's a right angle here, although the same answer would be obtained even if it wasn't directly above the right angle, if this C was anywhere above the base at height C. Okay, we're going to take everything as right angles. Now we're going to use the method which last time I called volumes by integrating cross sections. And as you can see, I've drawn a cross section. Now what we're going to do is we're going to let this bit here be of length x in general, and x is going to go from 0 to C, and for each x we're going to get the cross section, and I'll highlight it. And note that this cross section is parallel to the base because all the cross sections are perpendicular to the x-axis. That's how we require it. And so this is also parallel to the base, and this is a right angle too. And in fact, this triangle is a similar triangle to the base. Now let's mark some more things. The area of this I'll call A of x. The area of this as a function of x, and I also want to note that this, if this is x from here to here, and from here to here is C, then this bit, the remaining bit, let's say from here to here, is going to be C minus x. That completes x to C. Now, the way we're going to do this is we're going to, for each x, compute what A of x is, and that will be our next task, because then we'll be able to write the formula that the volume of the pyramid V will be equal to the integral as x goes from 0 to C of A of x dx. And as I said, our challenge is to find now these A of x. It's a right angled triangle, and if I just knew the two sides, then I could compute the area. So let's do them one at a time. Let's call this side here, we'll call it y. And I'm going to find y by the method of similar triangles. We have two similar triangles here. Let me highlight the smaller one, which is this, this, and this. And this is similar to the larger one, which is this, this, and this. They're similar because this is 90 degrees and this is 90 degrees, and this angle is common, and once you have two angles the same, then they're similar. And for similar triangles, then you have that the ratios of respective sides are equal. In our particular case, what I'm saying is that the base of this over the base of this, which means y over b, will equal to the height of this little triangle, which is C minus x, over the height of the larger triangle, which is this, which is C. And from this I can extract y, and I can conclude, and I'll write it over here, that y is equal to, just multiplying by b, b over c times c minus x. This is going to be one of two equations, because the other one I'm going to give another name to. Let's say we'll call that one z, or z if you're in England. And once again, we're going to have two similar triangles. the smaller one is going to be here, here, and here. Oops. I'll try again. And here. And the larger triangle will be this, this. Not doing very well with this, but you get the idea. And this.